Okay. Thanks a lot for the introduction, and thank you so much to all the organizers. This has been really fun. It's my first time here, and I'm having a really good time. I hope you're all having a good time as well. So I'm going to completely take you to a different world. Sorry. You can't? Oh, maybe I should put it closer. One sec. Is it better? Okay. Distance. All right, so I'm going to take you to a completely different world, to cryptography. So before that, the lab I'm coming from is called Quantum Software Lab, or QSL. It's in the beautiful city of Edinburgh in Scotland. So if you haven't heard of us, this is us. So I'm one of the faculties there, and we are the largest only theory quantum group in the UK now. And this is not even the most updated picture of all the researchers there. So consider, if you like looking for PhDs or postdoc, or if you just want to visit us, we work on a lot of different topics, all kinds of like theory in quantum computing. So that's that. What I'm going to talk about. So first of all, I will start with almost no math, and then as we move forward, we will see more and more math. So if you come for the math, please don't get discouraged by the first part of my slide. If you don't prefer math, I hope you have a good time in the beginning of my talk. So I have two lectures. In the first one, I will talk about a lot of conceptual things, like why we do quantum cryptography, why it's important, what is quantum cryptography, what is considered to be quantum cryptography, and all that. I have to give you some background on quantum information. The good thing is that my lecture is on Thursday, so you already seen a lot of this stuff, so I can just like go over them. And you have another chance to like review the stuff that you already learned. And then we're going to go over one particular protocol, which is called QKD, or quantum key distribution. And I will try to give you a lot of like details about what it is and why it's interesting and everything. Tomorrow, I will completely get rid of QKD, and I'll introduce you to a lot of other things, because many people think like quantum cryptography is just QKD, but there's like so much more in there, and there's so many protocols. It's very cool, and so I will introduce you all these like some of these different protocols. And the idea is that tomorrow you will see some of the interesting recent topics of research. So if you're interested in this field, you know where to look at, what kind of topics to look for. So that's the plan. Let's start. So, okay, so we have cryptography. Why do we need a new kind of cryptography? What's wrong with the previous cryptography? You probably already know the answer to that, but imagine you wake up one day and you see this like breaking news that now cryptography has been broken. It's gone now, like. And when this happens, you can be in two different worlds, two different imaginary worlds. Either you're in the world of panic and there's no cryptography anymore and there's no security and it's that, or you just see the news and you're chill, you're like, oh, fine, okay, like, we have other ways of doing cryptography. So we all want to live in world number two, because sooner or later, this breaking news will happen, and so we want to be kind of like safe. But why this can happen? Because of this guy. So Peter Shor in 1994, he came up with this algorithm that in the beginning had nothing to do with cryptography. It was like, okay, so I found like an algorithm that can solve factorization. And this is something that we assume we should not be able to do it efficiently, right? From a lot of like complexity theory and stuff. And then cryptographers be like, yeah, bro, but this is exactly what we made our cryptography based on, so it's bad, right? And yeah, Shor goes like, oops. But so that's the thing. So because of Shor's algorithm, we know that there is an efficient way in theory to break public key cryptography. I'm not going to talk a lot about that, because I think in the other lecture, which is about post-quantum, you will hear a lot about this like algorithms and how to deal with them. But so this is the reason why, basically, right? Okay. But so you might think this is a news story, this thing with the quantum happening and breaking the whole cryptography and like us needing to do a new kind of cryptography. But this is actually a very old story. So cryptography has always been about this never-ending battle between code makers and code breakers, right? from ancient time where you had Caesar cipher, which was like one of the simplest way of doing cryptography. You had a text and you kind of like shift letters by some constant factor, let's say 3, and you had a code. You had an encrypted version of that. And it was really simple, but in the Roman era, it was very effective. And then people got smart and figured it out. And basically, the code makers, they got like smarter, and they come up with like all kinds of like different complicated shift and substitution and things that, at least with the naked eye, it's a bit hard to break, right? And then, at some point, around 19th century, there was this Arab cryptographer who did this thing that was really cool, actually. And that was the first, I would say, systematic method of doing cryptanalysis. And it was like analyzing the frequency of data. So it's called frequency analysis. The idea is that when I write a text in a specific language, like each letter or word happened with certain frequency. So for instance, I use the word is a lot more than the word sophisticated in a text, right? So by analyzing and looking at this frequency, you can, even though you don't know the code or the shift, you can figure it out. And yeah, this I think was like really awesome. And so this is strike really hard on code makers, because this method could break a lot of codes. And then the battle continues. You all know about the word war. If you saw the movie Imitation Game, you know that there was like this really interesting thing going on between the Enigma machine and Alan Turing trying to break that. So and all that and goes and goes and goes till the modern era, which we find a really nice way of doing cryptography. So we do it really mathematically, very systematically. It's no longer heuristic. It has like really solid foundations. And this is doing cryptography based on a public key and based on some like mathematical hardness assumption. And for some time, it seemed that code makers have won, right? Till the quantum comes, and now we have to come up with new ways of doing cryptography. But what I wanted to tell you in this slide is the importance of cryptanalysis and cryptography kind of like together. And you get the best of codes if code makers and code workers collaborate. And this is, I think, an important message. Okay, so that was that. Okay, so we all know that we can do factoring, and we can also do solve another problem in quantum computers that's called discrete log problem. And this is basically all of our public key cryptography. So we relied our cryptography assuming that those problems have to be hard. But how real is this, right? So we know that in theory this algorithm exists, but is it real? Well, the thing is that yes, because now we have quantum computers that are scaling up, and we're getting better and better hardware. So we have like every day a lot of qubits, like news that's going on. Okay, now IBM has more qubits, Quantinuum have these qubits that are amazing, and all that. So there are a lot of different companies that are trying every day harder and harder to make quantum computers, not to just break cryptography, of course, to solve all these like interesting problems that you heard about, but as a consequence, this can happen. And the question is that are we not there yet? And the answer is no, we're not there yet. Otherwise, you would have seen the breaking news. But the reason that we're not there yet is that these devices are still very noisy. We need to run fault tolerant or error correction on them to be able to do something interesting. And we're not there yet. But we probably will. But the other thing is that during the past, I would say maybe 3 years, I'm not an expert in error correction, but the past 3 years has been really amazing years for error correction. People have come up with so much progress that the field has like progressed a lot, way more than we thought it would in 3 years. And so because of the devices getting better, and because our ability of correcting errors are getting so much better, this is getting closer and closer. And maybe the speed of which we think we can actually run Shor's algorithm is not the one that we think, right? So you can ask this very reasonable question that can I understand that with currently deployed cryptographic protocols, when I can actually break it with a quantum attack? And this is a really important question. And it's not an easy question to answer, because it's not just about knowing the complexity of these algorithms. It's also about a lot of details, like how much resources I need. Can I reduce these resources? Can I make it can I like make this a specific gate with like less actual gates on a hardware? So there's so many details, and also it depends on what kind of error correcting code you use. So this you might find interesting if you're interested in cryptography. There is an open source project by my colleagues in our lab that they try to actually answer this question. So there's this open source repository, and they call it Quantum Threat Tracker. And you can go and play around with it, and there's a QR code that takes you there. So you can plug different like error correcting algorithms and like different sort of like factoring algorithm and see like what number it gives you in order of like what sizes of, let's say, public key scheme it can break. So this is, you can track when this is getting closer. But the thing is, okay, even though we're not there yet, we know that we kind of will get there. And the thing is that we cannot start building up cryptography when it's completely broken. And there's many reasons, because building new cryptography is complicated. It takes many years of research to find out like best way of doing it. And the other important thing is that cryptography is not just theory. It's very important that the stuff we come up with, I mean, I'm a theorist. I can write down on a blackboard as many protocols and algorithms as I want to do cryptography, and it's fun, but it's not useful if it cannot be deployed and if it's not efficient. So it's very important. Like, you can come up with all kind of crazy cryptographic schemes, but if it's not useful, then no one will use it. And so that's why, even though if you have the theory, it will take a lot of like other many years of research to come up with efficient version of those. So it's a time-taking process. And then, even if you have all these like good things, it will take time to change the infrastructure, right? So now we build a lot of things around these cryptography schemes that we know for years, but we need to change them into new ones, and that will take time. And this is why many entities like governments, standards, institutes, even companies, they're all looking now for a solution, because it would be too late in the time that it's actually broken. So what options do we have? Usually, people think that there is like a branch, right? So there are two ways that you can take. One of them is that, okay, so we find new assumptions, we find new mathematical problems that are hard also for quantum computers, so that you cannot break them with quantum computers. We don't even know if there are such algorithms, but we strongly believe that they exist. And the other idea is that let's use the thing that made our life miserable to help us to actually make cryptography. And that's why I call nature breaks. Quantum mechanics leads to break, but quantum mechanics also can help us to build cryptography. In the community, a lot of people call this side post-quantum cryptography and that side quantum cryptography. I personally think, because I love this picture, you should use best of the both worlds to get like really innovative and cool and practical schemes. But yeah, historically these are like separated in this way. So the idea is that let's use quantum mechanics, which is now in the hand of the bad guys to break system, to be in the hand of the good guys. And the key here is to find the balance between the power and limitation of quantum adversaries, because it's not like that a quantum adversary is only powerful. There are things that you will see in this lecture, hopefully, that you see that it also causes like some limitations, and also help us to pose limitation on the adversary. So here, even I would say more than classical cryptography, this balance between quantum cryptanalysis and quantum cryptography is really important. So you can only create good schemes if you understand what adversary can do in the quantum world. So that's that. And but the main idea that leads to this is that we have a lot of interesting properties that come from quantum mechanics, quantum information, and we want to somehow use this property to construct cryptography. Okay, so what is the landscape of quantum cybersecurity, as some people call it, or quantum cryptography? I took this picture from this paper by my colleagues. So you can think of it as this way, that we have the honest party and we have the adversary. And for the adversary, we assume the full power. Like, so let's assume the adversary can do anything they can do on a quantum computer because we want to be as paranoid as possible and come up with the best schemes as we can. For the honest party, if you can only do or you want to only do classical stuff, then you're in the world of post-quantum cryptography, which I told you about. If you don't have a quantum computer, but you have some quantum devices, you're in this regime that some people call quantum enhanced, which is mostly the stuff I will talk about. You don't need full quantum computers to run protocols on a quantum network. You need some quantum devices. And the day that you will actually have quantum computers, good guys can also use it so that you can run more sophisticated or more complicated cryptographic functionality, things like blind quantum computation and things like that. I will not talk about those today, but this is a regime where you have a full classical infrastructure and then you have a full quantum infrastructure, and they play around. When we move to the quantum world, there are many things that need to be changed. So the first thing that changes is definitions, right? Because the definitions of the security always have a particular description of an adversary in mind, or some assumptions on the adversary. And those assumptions or description will change. So you need, in many cases, to change your definitions. Then you need new primitives, which means easy or small or fundamental protocol where you can use as a building block to build like larger and more complicated things. Then you need new quantum protocol. And then, as I said, you also need new algorithms. Like if you really want to do serious quantum cryptography, you also need to be really good at quantum cryptanalysis. And here you can use a lot of things. I've done some work on how we can use quantum machine learning to, as an attack for quantum systems and things like that. So these are everything that needs to be changed. Okay, so now let's get a bit more in detail. What are the properties of quantum systems that we can use? The first one, superposition and measurement. So you heard and listened to this a lot, so I will do very quickly. So you have a classical bit that can be 0, 1. You have your quantum bit or qubit. Now this qubit is, as opposed to this like 0 and 1 or bit, it's more like a vector. You can always show it on a sphere, and it can take positions in this sphere which are like linear combination of the bases, right? So if you have 0 and 1 as your bases, then you can have this state that's called plus. Measurement, it's when you measure an unknown quantum state, which is like a closed envelope, it's a probabilistic process and you disturb it, so when you open it, it's a different state, right? So you disturb or you collapse the state into something different. Like for instance, if you have this like unknown vector that's pointing out somewhere and then you make it collapse to the direction of x and z, you get the component of x or the component of z, and this is a probabilistic process, right? So if you have superposition of measurement, that comes straight from quantum mechanics. So is it good for us or bad for us? Yeah, so a bit of both. First of all, by the way, this is important for me personally. Who knows which movie this is from? Yeah, good. I don't have because I was giving this talk at some point and the audience were, I think, too young, and I put this and everyone was like, what? And I was heartbroken personally, so I'm very happy. I'm talking to the right audience. Okay, so why both? So superposition is one of the most important, if not the one, it's one of the most important components in quantum algorithms that have a speed up. So we use it a lot. So in that sense, it's bad for us because if you have a speed up, it means that yeah, you can break things. But you have also measurement, which because it's probabilistic and destructive, most importantly because it's destructive, it changes the state. So if you have something encoded in a state, if a bad guy looks at it, it changes it. So that's good. That's good for cryptography, and you'll see why. But it's also a little bit bad because it's bad for us. Because if I have a state and I somehow kind of like want to verify it, then I also disturb it. It's not something that anyone can escape. So you need to be really smart on how you use measurement. But if you combine superposition and measurement, so if you look at both of them together, then you get something really, really beautiful that's called conjugate coding or conjugate basis. And this is really good for quantum cryptography. we will do a lot of things just with that. So what is conjugate basis? And I think this is the most important thing in my whole talk that you need to learn, because if you learn this, you will learn QKD, I think, and you will learn a lot of the stuff that I will tell you tomorrow. So if you have any question about this slide, ask me now, because this is going to be very important. Okay, conjugate coding was introduced by Stephen Wisner. Wisner? I don't know what's the exact pronunciation. He's a very, very, very interesting character. So Aronson has a really interesting blog post on him. Go and read it. He's very fun. Was very fun. So in order to tell you conjugate basis, I will use this representation of qubits called Bloch-sphere. You might have seen this in the other talks, but I will go over it again, because if you're going to work in quantum information or anything like related to that, this is going to be your friend. This is really good, okay? So Bloch-sphere is just a way to represent all the states of qubits in a sphere, and the reason is that the group of SU2 can be represented as a general rotation on 3 dimensions on a sphere. So you can treat like every axis as one basis, and you can rotate between the bases, right? So you have 0 and 1, which we usually call Z bases or computational bases. And if you go to the X bases, you get the equal superposition of 0 and 1. And you're in the X bases, and you can do the same thing for Y. And you have things called Pauli matrices, which again, I think you've seen in the other talks. So these are a family of matrices, X, Y, and Z. These are bases for qubit operations. So these are a full basis. You can describe any operation on qubit space with them. But also, their eigenvectors are a basis for qubit states. So what I mean is that, so Z acting on 0 state, which is its eigenvector, will give you 0. Acting on 1, it will give you state 1 with eigenvalue -1. And it goes the same for X on plus, and I skipped the Y because it's similar, so Y on this Y plus and Y minus, right? So usually when you write a general state of the qubit, you write it as alpha 0 plus beta 1. And this is usually so this is the computational basis, this is the usual notation. You can also write it using Bloch-sphere and basically polar coordinates in terms of angles of the Bloch-sphere. So this is something you can do. But you can also write any general state of the qubit in the basis of plus and minus. So it will be different coefficient, but it will be alpha prime plus and beta prime minus. So this just show you that these are the full bases. But now the interesting thing is the measurement. So if I have a state plus, and I measure in X bases, right? Because plus is eigenvectors of X, you get with probability, so if it's plus, you get with probability 1, the state plus, and with probability 0, the state minus, and if it's minus, it's the other way around. So you always get it right. But if I have a state plus, and I measure it in the basis of Z, you get 0 and 1 with probability half, right? But why this is important? Because if you encode things in Z and you decode in Z, then you always have a deterministic answer. Or if you encode in X and decode in X, you always have a deterministic answer. But you encode in something and decode in the other one, so X or Z or the other way around, not only you get a probabilistic answer, but you'll get a uniform distribution, which is really good. So you kind of like, you know, the false answer has no information somehow. We will get back to this. But this very, very, very simple thing that only needs understanding of a qubit is the basis of conjugate basis or conjugate coding. Do you have any questions? Now is the time to ask. Okay, so everyone got the idea. Very good. Another property that is very important, and you also saw it before, is that we have no cloning. So classical information you can always copy, quantum information you cannot copy. The thing is that, so the reason I put this slide again, because I wanted to tell you the exact a statement of no-cloning theorem. So the statement of no-cloning theorem says that you cannot create two perfect copies of an unknown state. So these two parts are really important. Because, if it's not the case, then you have different results, let's say. So again, you can see that a lot. Is that good for us or bad for us? So in general, no cloning is really good. No cloning is our friend in quantum cryptography, and many, many protocols, directly or indirectly, their proof relies on the fact that you cannot copy quantum information. So it's really important. It's like a fundamental thing in quantum cryptography. But also, no cloning makes our lives as cryptographers sometimes harder, because you cannot copy information. There are a lot of concepts and techniques in classical cryptography which does not carry over to the quantum. Like, for instance, you have this very cool and nice concept in classical cryptography called transcript. This is you can look at everything that's been written over the channel ever, and you can take that as a message, and then you can play around with it to do proofs. And this is called transcript. And this doesn't really exist in quantum, because you cannot assume that you have that. Like, there are no cloning, so you cannot make a copy, and there's measurement and things like that. So yeah, it makes your life harder to do proofs and to, let's say, define proper definitions, but it's very useful for cryptography. Another thing I wanted to tell you about no cloning, and this is related to another topic that I really like and I'm really passionate about, which is learning theory, is that no cloning has a very interesting relation with learning. And I will not go very deep in that because it's a long conversation, but I will just show you a flavor to see what I mean. So when you have a quantum state, this is, first and foremost, this is a physical system. Right? It's not just like a vector, right? So you also have a vector representation, but it's a physical system. And what no cloning says is that if you don't know what this system represents, then you don't have a unitary operation that takes you to perfect copies. Okay? But we also know if you have the description of a state, you can prepare as many copies as you want. This is not in contrast with no cloning. So you have this regime between no information and full information, and there are actually things in between. So if you have more and more information about what this unknown state is, so for instance, if you know which class of a state it comes from, you can do sort of cloning. So you can do approximate cloning, and this is possible. Quantum mechanics allows you to do that with some threshold. And the more you get information, the better you can clone intuitively. And approximate cloning, which is on its own a subfield of quantum information, has a very interesting relation to tomography. So tomography is exactly when you have an unknown state or a system, and you want to know what's this state, right? So you need a lot of copies to measure, to get some statistic to conclude what is your state. So this is tomography. But tomography is a notion of learning. So in learning theory, there's a way that you can describe tomography as a learning problem. And this learning problem takes as input copies of an state, and as an output, it gives you a classical description or a good estimator, if you like the statistical lingo. And this is a learning problem. And exactly these nuances between the cloning and learning, they are related together, and this is very cool. And this is something that is also important in cryptanalysis. Okay. There are some other properties that I need to show you, and I think they're important. But before I do that, I need to tell you a little bit more quantum information. Again, some of this is stuff you've seen, but review. So this part is easy. So you have a state of qubits, then you can go to higher dimension. You have d-dimensional Hilbert spaces. You have n qubit, you have 2 to the n dimension Hilbert spaces. The important part the reason I put this slide again is to tell you again about the composite system. So in quantum mechanics, basically you can have a physical system and you can have another physical system, and there's actually a proper way of talking about both of the system together, and this is by composing them through tensor product. So the way you do it is that this new bigger space of Hilbert space of A and B, it's constructed by the product of the dimension. So the dimension is the product of the dimension of the two space, and its basis is constructed by tensor producting the basis. All right, so that's how, and that's why you can have like composite system. Right. So you've seen in all my previous slides the bracket notation or the wave function formalism or the vector formalism, and you've heard before in the talks on Monday at least that this is not the most general way. There are things, there's like another formalism that's more general. And I thought maybe it's a good way to tell you why this is more general, why we needed like another formalism to talk about quantum state. So reason number one is we want to talk about subsystems, right? When you, in the previous slide, I showed you that you can tensor product the bases and you can get a bigger space, H of A and B, right? But this space includes more than just the tensor product of the bases, because it also includes superposition in that larger basis. So it includes things like this entangled state, which is you're going to see a lot in my talk. This is called Bell pair or EPR pair or just maximally entangled state. It's a superposition of up, and down, or up, down, and down, up. You know, you can have like different combination, but like it's that. Or 0, 1, 1, 0. The physicist likes this way, computer scientists like 0, 1. So the thing is that now, if I have this system, so if I have a physical system that I can tell you that this is its vector, then what is the state of the subsystem, right? So the state of the subsystem A is not 1, neither is 0, and it's the same for B. It is something else, right? And if I stick to the vector formalism, I don't have any way to describe that. So there's another way to talk about that. The second reason is that you might want to talk about ensembles of a state. What do I mean? So let's say I have a bag, red bag of a state that produce a state red. And I have a green bag of a state that produce a state green, whatever that is. And if you sample from that by 40% probability and the other one by 60%, then you get a state which is a classical mixture of states, right? And you can't just describe that in a vector way, but there's a nice way to describe this like classical mixture. This is by density matrix. So this is the second reason. And this is the formalism with which you can do both of the things I told before. So a density matrix is basically a linear operator that's defined on the space of so it's in the linear operation on the space of a Hilbert space of dimension d, maps it to the same Hilbert space, and it has these three properties that is important. So it's Hermitian, it's trace 1, and it's positive, right? Why we need all this? Because we want the eigenvalues to be real, positive, and normalized, because that makes this a physical thing. Otherwise, it has nothing to do with physics, and we want to describe physics with it. So once you have that, you can represent it by a d by d matrix. Like, for instance, if you have a vector of 0, 0, which you can write it like that, the way to get the density matrix of it is by doing this like basically ket-bra notation. So you do this like product, and then you get a matrix. So this is, this exactly describes the same system as this one. It's just that this is with a vector, this is with a matrix. And back to our beloved block sphere. How do you talk about the states here? So this is surface of the block sphere is the space of all pure states, as we saw before. Like all the vectors, for a qubit, you can describe it like that. But everything that's inside now has a meaning. These are all density matrices. So, you know, everything that's like included in the density matrix of the state. And the center of the sphere is this very important state called maximally mixed state. It's basically the classical mixture of any two bases, for instance, 0 and 1. So it's half 0, 0, half 1, 1. And you can write it as identity over 2. In general dimension, you can write it as identity over d. Questions? No? We're all good? OK, let's go. So how do I describe subsystems? I promise you that we can do that. So let's go back to our maximally mixed state example. So this is a vector of a pure state that describes the maximally mixed state. In order to get the subsystem, first you construct the density matrix of the pure system, which is this guy. And then the formalism tell you that if you basically, do you remember I told you that, that by tensor producting the bases you construct the bigger space? So if you trace over the part, like the basis of the system that you don't want, like for instance here, I want to talk about A, so I trace over subsystem B of the whole density matrix. Then what I get is a density matrix that describes the subsystem A, and the same goes for B. And this is called reduced density matrix. It's basically like you hide the other subsystem and you don't look at it. It's not like you measure it, right? It's different. It's not a measurement. It's like I care. I only care about this part, so I only want to look at this. So that's called tracing out. But yeah, so these systems are still related, so the effect of this exists here, but it's just that I don't look at it. So this is a way to describe subsystem. And to describe mixture is easy, so I didn't put it here, but it exists here. So you can create any mixture you want by, just like doing probabilities between the two bases. So this is that. And now the thing is that if you have a general system that is separable, then you can tensor product the subsystem. So it can be described by the tensor product of the subsystem. And if it's not separable, then you don't have this property. And this is actually a nice way of knowing if you have entanglement or not. If you can figure out if you can write it in a tensor product form or not, you know that if you have entanglement or not. And I don't know why I put this probably, but I thought this like cyclic property of trace, if you forgot about it, is so important in the proof that proofs that you might need to remember it. Anyway, but now the thing is that the idea is that so now I have one formalism to talk about all kinds of a state that I want: pure, mixed, entangled, non-entangled, and that's that. Okay. So that was about generalization of states. There's also generalization of measurements. So you've seen measurement, you've seen like how you get probabilities out of measurements. You can have a generalization of what you probably saw before for observable. So if I have an observable, the Born rule, the actual Born rule will tell you that, okay, so your projector, which are your measurements that you saw before, are the eigenspace, so you can construct them from the eigenvectors of your operators, and then the probabilities will correspond to the eigenvalue you get from the measurement outcome. So this is same as what you saw. So basically you have your projection operator, Pi, and whenever you like sandwich it between the state, you get the probabilities, and then you can also find the post-measurement state quite easily through that. So this is what you had before. But the generalization is that you don't need to only have projection operators to have measurement. You can have non-projective measurements as well. These are called POVM, for positive operator valued measurements. And basically you relax on the projection, although you still need that the sum of them sums up to identity. This is important for probabilities eventually to sum up to 1. And then you want kind of like the same construction. So when you trace over the operator acting on the density matrix, you get the probability. So this is generalization of Born rule, and these are POVMs. But why did I need POVM? Why projection was not enough? So again, because I want to talk about subsystems, so measuring subsystem, you can do it really nicely using POVM. Oh, sorry. So you can write these two operators that basically are, so let's say I only want to measure subsystem A. I think there's a typo. Yeah, sorry, there's a typo. But let's say I want to only measure the subsystem A. So I can do basically nothing on subsystem B, and I can do a 0 or 1 projection on subsystem A. So this should be B. So these are that. But the more important maybe reason is that you can define measurement scenarios which you cannot describe by just projective measurement. Let's say I want to do this. Let's say that I want to have a measurement that if it's case 1, it will give me a state 1. So I know that I have a state 1 for sure. And if it's case 2, so if I get outcome 2, so I have only 1 qubit, but I'm defining 3 outcomes. And my outcomes are as follows. 1 meaning I have a state 1, 2 meaning I have a state 2, 3 means I don't know, right? Why do you do that? Because with that, you can have a scenario in which when you measure, you either know exactly the result, you don't have a false positive, let's say, outcome. But of course, you cannot, because of the probabilistic nature of the quantum mechanics, you cannot always be right. So the third question is that the third option is that sometimes you cannot tell me which state it is. So you can define 3 operators, POVMs, that sum up to 1. And the way you construct them is that basically for the first one, you project into the orthogonal of the other one, and for this one the same. And then you mix them with some like value, with some like coefficients alpha and beta. And the last one is obviously, because they sum up to 1, they need to be 1 minus M1 and M2. And if you optimize over these parameters, you can minimize the probability of getting outcome I don't know. And this is related to a cool problem in quantum information called unambiguous state discrimination. It's exactly what it means. So if I want to discriminate between 2 things, if I use this kind of measurement, I'm not ambiguous. Like, it's not like if it was 1, sometimes I could wrongly tell you that it was 2. It's that I always know, but sometimes I don't know. So that's what it means. OK. Now, we can go and look at the rest of the properties. How much time do I have? All right, good. So these set of properties are about entanglement. So maximally entangled states, the one that you saw, they have these interesting properties. The first one is actually the property of the entanglement, which if you prepare this kind of states, you can also separate them physically, and now you have some sort of correlation in distant places. These are like non-local correlation. The interesting thing is that this will affect the statistics you see, right? So if you do this experiment, you get some statistic, and this statistic can tell you that things are local or non-local. And this is a very cool property. It's important in foundation, but it's also used in cryptography a lot. Second thing is that if you look at the subsystem of a maximally entangled state, and that's why I showed you how you can get subsystems. So I wrote the full, like, a state of EPR, so I just like, wrote the full thing, and I put A and B so that you know which subsystem is which, right? So now if you calculate the reduced density matrix, and I wrote down the full calculation so that you see it's very easy, you get the maximally mixed state. And same for this one. So the subsystem of a maximally entangled state are maximally mixed. And this is really important because it means that the subsystem don't really give away any information. And we're going to use that a lot. So this is good for us, actually. Another good property of this state is that it doesn't matter in which bases you write them, they're always maximally entangled. So if you write them in 0 and 1, and then it has this form, if you write them in plus minus, it has also this form. So it's just like its properties is basis independent, which is, again, very good. We're going to use that. The fourth property of maximally entangled states are that they're monogamous, or we have something called monogamy of entanglement. What it means is that if you have a maximally entangled state and you know that you have another system, so if something, let's say, between Alice and Bob is maximally entangled, and then you have someone else, what you know for sure is that if this is maximally entangled, the state of the last system, it has to be separable to this, right? So if A and B are strongly correlated, they don't share correlation with a third party. We know that they share correlation, that was not maximally entangled. And again, this is useful in security proofs. Okay, another property that's going to be very useful for us, it's distinguishability between the state. I talked about this a little bit when I told you about the POVM. But now we can like look at it as a game. So let's say I give you a fixed set of states, and these are known beforehand. And it's a game between Alice and Bob. Alice chooses one of the states, send to Bob, and Bob needs to guess which one it is. Right? It's as simple as that. And what quantum mechanics tells you is that non-orthogonal state, they cannot be distinguished perfectly with certainty. Right? So you have like always the probability of being wrong or not knowing. We have questions? No, okay. Yeah, so if you want to see the proof, it's really easy. We can take the easiest case of having two states, psi and phi. I assume they're non-orthogonal. I take any general measurement that I want. And then I assume that I can distinguish them perfectly, meaning that I assume if I have psi, if the state has been psi, and if I measure with the first one, I get that with probability 1. And if it's the other one, I get the other one with probability 1. But now, also because of the properties of POVM, which I have to sum up to 1, it means that the other, so if you have psi and then you have the other measurement, it has to, like this overlap has to be 0, right? And now you can write, so remember I told you can like write the states in any basis you want, so I can write psi in the basis of phi. Well, I can just do that. So I take phi and it's orthogonal, and it has a description. I don't know what it is, but you can write it like that. And the important thing is that here, because I assume that these are non-orthogonal, I need to have an alpha here. But if you write this down and sandwich it with this, then you will see that alpha has to be 0, meaning that they have to be orthogonal, which contradicts my assumption, which means that they cannot be distinguished perfectly. Okay? So distinguishability. Then for general mixed state, quantum information has a limit on how well you can discriminate things. And this is called Holevo bound. And this is, again, I think one of the most interesting and most important theorem in quantum information. You can quantify how well you can discriminate the states by, if you have the density matrix, if you basically calculate their distance, so this is called trace distance. It's a notion of distance, it's the L2 norm between two matrices, and it's a notion of distance between quantum states. So if you calculate the distance, then you can know the optimal probability with which you can discriminate this state. Remember the theorem? Tomorrow we will use it directly for something. I will recall it again, but just. Okay, so now I'm ready to introduce you to your first quantum communication protocol for people who have not seen this before. Any questions before I get into QKD? Okay. Good. Let's go. So before I tell you about QKD, quick note is that usually we have two types of security. I mean, you can have more, but these are the two main types of security you have in general in cryptography. So all the stuff about having assumption and like basing cryptography based on assumption is in the first part, which is computational security. So usually you rely on some assumption. And well, your security may or may not break depending on if that assumption holds. We have like really good schemes there, so we're still interested in computational security. But there's a stronger notion of security that's called information theoretic security, and that means that I don't put any bounds on the power of the adversary, basically. That's why it's called information theoretic. It means that it's only bounded by whatever information property that is there. And this is very, it's also called perfect security sometimes. This is very strong, but for the same reason, not so many things can achieve this. Okay, so, but this exists in classical cryptography. Let me show you something that has information theoretic security. This protocol is called one-time path. The way it works is that you have Alice and Bob, and you want to send a message from Alice to Bob, but there is Eve, and Eve can read it. So let's assume I want to send this secret message, which is the name of this cool summer school that I want to go, and I turn it to binary, and I want to send it to Bob so that Bob can also attend, but I don't want everyone to attend, right? So I want to keep it secret. I can do that if Alice and Bob have a key that has these two properties. So first of all, it's a random sequence of bits, and it's as long as the message. So if I have these two properties, then there's a really beautiful, extremely simple classical protocol. The way it works is that you just XOR bit by bit the message with the key, and then you get your encoded thing, which is in cryptography called ciphertext. So you get your ciphertext. And the reason that this is encoded is that by properties of random strings, if you XOR anything with a random string, it remained like the XOR thing is also completely random. So if the first key was completely random, then my cipher key is also completely random. And as long as Eve doesn't know the key, they learn nothing about the message. So how Bob decodes? If he has the key, which he has, he XORs the ciphertext again with the key. Then basically you have M XOR K, these two cancel out, and you get the M. So you get the message. So it's like extremely simple, the encoding and the decoding both. But this has information theoretic security. I don't need to rely on any power of the adversary here. I only need to rely on the fact that this key is on both sides, no one else knows it, it's as long as the message, and it's random. Do you see any problem in this? Yeah, so I mean, we assume they're not different, but yeah, so it's kind of like along the correct way. True, that's also a problem. But there's a more obvious thing which is related to what you said. Sorry? C is the ciphertext, is the encoded message. No, so you send the C over the channel. So this is.
Send the C to Bob directly.
Yes.
Okay. I thought it was Charlie.
No, you just like this is your encoded message. You send it over the internet.
You have to send the key, which is as long as the message, and it's quite a big subspace.
Exactly. So the problem is that how do you send the key in the first place? So if you have something that needs to be secret, and it's as long as the message, it's kind of like the same problem as sending the message. So it's like a chicken and egg problem. So this is really cool, really simple, really beautiful. The problem is that how do I do this, right? And you can't say, okay, we meet one time, and then we share the key, and then we go home, and then we can use it later. But as you said, also, the problem is that this protocol is perfectly secure only if I use this once, so which makes it a bit like ridiculous, right? And this very, very simple problem has been long standing in cryptography. People were like, okay, well, how do we do this? And that was one of the main reasons people have started to think about new ways of doing cryptography and come up with public key protocols. But the thing that we're going to do, and the thing that I'm going to teach you, exactly solves this problem. So in a way, it gives you a way to share long keys with information theoretic security, and not only if that Eve in my previous slide is classical, but if it's quantum. So now you have a much more powerful adversary, and you still want to do this. So lots of good things about QKD. For first thing, as I said, and you saw in my chart of quantum cybersecurity, this doesn't need full quantum computers. You can do it with small devices, whatever that means. It can be sometimes like some companies like ID Quantic, they create these QKD devices, so it's kind of compact and small. Most of the time, these are optical tables in a lab. So it's not so small, but it's still much more minimal than a full quantum computer. Then it's available today, meaning that those pictures are real. And you can also do it over long distances now with satellites. And lots of countries have their satellite QKD program. Scotland has one as well. So it's something that people do, and they're trying to make it better and better and better. And QKD has a property that a lot of computational security type protocols don't have, and it has a forward security, meaning that it's not if you can break the cryptography at some point, then your previous messages are also insecure. That it's not like that. So it has this very cool property of forward security, or everlasting security, sometimes people call it. I like forward security more. Anyway, so it has also lots of bad properties in some sense. I'm not talking about this so much because I want to show you the protocol, but it's really, really not as feasible as your normal cryptography. Like you can't put it on your phone, for instance. This is a main important issue, and lots of other things which I will mention slowly, but yeah, bear with me. Okay, what do we need for QKD? So one of the misconceptions in our field is that sometimes when people teach us QKD, they say, okay, you have a protocol that only relies on nature. You have no assumption. First of all, this is not true. There's no such a thing as no assumption in cryptography. There's always an assumption. So I will tell you some of the assumptions and requirements, some things that we need to do in order to do QKD. So you need quantum mechanics, first of all, meaning that, well, yeah, if one day it turns out quantum mechanics is not true, it's not that you cannot do QKD because you still can do it in the lab. It's that our proof doesn't hold anymore necessarily because it's based on all those properties of quantum mechanics being true. Then you need the ability to prepare a state, and I'm talking about the simplest version of QKD, not all the versions. There are many different versions. So you need the ability to prepare states in Z bases and X bases. You also need the ability to measure in both of the spaces. You need a channel to send this state over. It doesn't need to be secure, that's the whole point. It's insecure, but you still need to send you need to have it. And that's kind of limits the types of quantum system you can have, so you cannot send superconducting qubits over the channel. That's why most of the QKDs are usually with optical devices. And fifth, and the most important property that you need, or assumption you need, is that you need a classical channel that is, again, not secure, because that's the whole point, but it's authenticated. Authentication means that I know the message is coming from you. So if I'm talking to you, I know that the message is actually coming from you. It doesn't need to be secure. It doesn't need to be encrypted, but it needs to be authenticated in the sense that I know I'm talking to you, I'm not talking to someone else. And usually, you just assume you have that, right, for QKD. But then you need to later think about why, how you can construct this. And this is one of the reasons that QKD is actually not a protocol for key generation. It's a protocol for key expansion somehow, because lots of times you need to start with a small key and then do the QKD and have more keys. But yeah, for now, let's forget about that. I will come back to that. And the setup, again, is simple. It's the same as before. You have Alice and Bob, and you have an adversary. The only difference is that this adversary now has quantum power and information theoretic, so it's unbounded. Why is that moving? OK. So what is the QKD? It's super simple. The way the protocol works is that Alice picks 2 random bits, a sequence of them. But for now, let's think about one of them. 2 random bits. One of them selects a value, the other one selects a basis, right? If I have the basis bit to be 0, meaning that I'm preparing something in the Z basis, if it's 1, I'm preparing something in the X basis, or plus minus basis. If the value is 0, the qubit I'm going to prepare is going to be either 0 or plus. If it's 1, it's going to be either a 1 or minus, right? So I just flip coins, get a string, prepare a state, and I send these states over to Bob. So Bob selects 1 random bit per pair. With that random bit, he also selects a basis. And that random bit has nothing to do with Alice's bit, right? It's independent. Now, they measure all these qubits that they received in that basis. And when they measure, they get an outcome, right? So when let's say, I don't know what the state it is, but let's say it was 1. When I measure it in a Z basis, I get the value 1, right? So I record it as 1. If it was the plus minus, also you can record it as 1, 0, and 1. So you get a bunch of sequence of things, right? So now I have AI, XI, BI, YI, and X and Y are the basis value. Now Alice and Bob are going to publicly announce the values for the basis, right? So Alice will say, I encoded in X, Z, X, 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 Z, X, X, right? And Bob will announce as well. And what they do is that they will only keep the places in which the bases match, and they will throw away the rest of the stuff. But in the places that they match, they're going to have a key. I'm going to show you why in a bit. And then they have to do some other things that I will tell you as we go on, things called parameter estimation, and then some classical post-processing. But the main quantum part of it is till step 5. Okay? So let's see an example. Let's say AI was 00110 randomly, right? And basis was that. So if you have basis 0 and you have 0, you encode in 0. If you have basis 1, you have 0, you encode in plus, minus, 1, plus. So these are the qubit Alice will send. Now Bob measures, let's say in this random basis, 00110. So if I measure this in Z basis, I always get 0. If I measure this in Z basis, it's random. So now it has been 1, but it could have been also 0. This is deterministic 1. This is 1. So on and so forth. So when this line and this line match, I will have a bit of a key. If they don't match, I don't have, right? And the reason is exactly, do you remember conjugate coding? If your basis of encoding and measurement match, your answer is deterministic. If it's not, your answer is random. And that's basically it. That's it. So you only keep places in which you have a deterministic answer. Why Eve doesn't know it? Because even though Eve knows the basis, because it's public, Eve still doesn't know the value. So the value is kept secret between, for Alice, for herself, and Bob. It's just that we know that it matches, right? And it's like that bit is independent from the basis, so the value can be 50-50. So this is why. Okay, what was this parameter estimation phase? The thing is that because there is an Eve on the channel, Eve will try to do some stuff, and we will see in a little bit what kind of stuff, but Eve will try to do some stuff, which means that Alice and Bob will perform some sort of check to see if someone is eavesdropping or like listening to the channel. And what they do is that they select a random selection of the bits, and for those, they will announce the value as well, right? So that will kind of like mess up with their key because they lose that like parts of the key because they announce it. But they can also use that to check, because if now both of the value and the basis match, they know that it's safe, and if it doesn't match, it's not. And you take this ratio, and it gives you a quantity that people in the community call qubit error rate, QBER. And this is basically it gives you a quantity or a threshold to know how good you're doing with your QKD. So if you're lower than the threshold, you're good. It means that you can extract a perfectly secure key, so you proceed to the classical post-processing, which I will tell you about later. If it's larger than that, it means that there's too much eavesdropping. Like, I cannot trust this key, so I have to throw it away and restart over the protocol. And this threshold for BB84, which is the protocol, the version I told you about, is 11%. So if you go over than that, then it's bad. Okay, so let's get some intuition about, so this is not a proof, but I will go step by step close to the proof. So what can Eve do, possibly? So they can measure the qubit and try to learn the information, right? Why this doesn't work? Because whenever they measure the qubits, basically the qubit is lost. And then, Alice and Bob will know it, so they can detect it. So QBER is like one of the reasons that you can detect such a thing. Then Eve can try to copy the qubits, and it's good that we learn all the properties, because now we know that because of no cloning, you can't do it. You can't do it perfectly. Even if you try to do approximate cloning, I'm not going to go over that, but there's a very cute proof that shows you that if you try to do best approximate cloning that's possible for this set of a state, it will give you a bound that matches the qubit error rates that you have for QKD, at least for the individual attacks. So this is kind of nice that these things match. You can do something that's a little bit smarter. You can, like Eve can try to measure the qubit to try to extract the information, but based on the measurement outcome, prepare a state again and send it to let me show you, to Bob. So basically, we have Alice and Bob, and the qubit goes here to Eve, who is sitting on the channel. So I measure it first, I get some outcome, but then also I prepared like another state based on my outcome, so it's E, and then I send it to us. So now Bob will receive some qubit, right? So it's not lost, and but Eve doesn't know all the information, so this is like sometimes goes wrong. Why this doesn't break? Because you can do the analysis of this attack, and you can see that this gives you a qubit that's higher than the thing that you can actually do, so it's good. It means that if they try to do this, it's detected. So yeah, so this is exactly what I have here. Do I need to pull this up? Do you see that? Okay. And so if the analysis of this is not too hard, so you can say that if Eve chooses the basis correctly, basically the qubit she will send matches to what Bob expects. So it cannot be detected. But also Eve can choose the wrong basis, but it still send the right outcome, because when they measure, they get the right one, and they send the actual one. So you can see that the probability of Eve winning, if they do that, is that in the correct basis, well, they win with probability 1. This is for 1 bit, by the way. If they're wrong, then it's the probability that Bob gets the correct outcome. So this happens with probability half. This happens with probability half. Half is 3/4, meaning that if you put the qubit at 1/4, then you can do that. So this is per bit again. Okay, so the intercept resend attack can happen, but we can detect it. It's good. It's all good. But this is frustrating, right? Like, do we need to really go over all the possible things that Eve can possibly do? And like, how are we sure that we're not missing anything? So this is a really bad way to do proofs. It's good to get some insight and intuition, but this is not a good security proof. We need a better way. Does anyone have an idea what property I might use to get this proof? Yes, kind of. So I'm going to use that in the next protocol I will show you, but even for the, you're kind of right. So basically the idea is that correlation is the key, right? Even between when you send the BB84 state, which are separable and they're not entangled, they share, there's a specific correlation between the bits of Alice and Bob. And this is the key to do the proof. So I'm going to use this property to do a formal, nice proof. So correlation, it has to do with the amount of information. So the properties that I'm going to use to do the proof are things that are basically classical information theory properties, or like quantities, and also the quantum version of those. So just a quick recap on the things that we're interested in. Classical information theory, you have a bunch of entropies. So entropy are a way to quantify information. So Shannon entropy, which is this like nice, cute expression, it quantifies somehow the average information in a random variable. You can have information of some random variable depending on the other one. This is conditional entropy. And the one that's going to be very important for us is this guy, mutual information, which is the amount of information obtained from one random variable observing the other random variable. And this can be written in terms of like these two basically. Sorry, not these two. The joint entropy and the entropy of the individual. So this is this plus this minus the joint entropy. And then there's this like relative entropy, which I'm not going to use, but for some reason I thought it's important to have it on the slide. Anyway, so entropy quantities. Okay? Questions? No? So the way we're going to do, again, intuitively still, but a bit more formal, the proof of QKD is to show that I have more correlation between Alice and Bob than I have possibly between Alice and Eve or Bob and Eve, right? So it was not possible for Eve to make themselves too correlated. And then you can put that like threshold of correlation you can possibly tolerate for Eve as your qubit, and then you have your proof. If this is the case, so now the nice thing is that I can tell you that you can think about all the information of Alice as this like pairs of beta string in this like big beta string of A. You can do the same thing for Bob, and you have the same thing for Eve. And what I want is the mutual information between Alice and Bob being bigger than mutual information between Alice and Eve. So it gives me an inequality, and I can use it to bound things. And if that happens, then my classical post-processing will give me a perfectly secure thing. If that doesn't happen, the classical post-processing doesn't help. I need to throw away everything. So the classical post-processing step, which I will not go into a lot because I don't have like much time, are these two steps. So first one is called information reconciliation, and the second one is privacy amplification. Basically, the first one is some sort of classical error correcting code, just to get rid of some noise and extra things. And the second one is to ensure that you actually have a perfectly secure key from a raw key. So raw key means these bits that comes out of the QKD protocol before I do anything on them. So this is raw key. There is like something really nice and easy I can do on them to get the perfect secure key. And that thing for people who know classical like cryptography a bit is hash function. So I just like hash these two raw keys with a very particular hash. It's called a 2 universal hash family. And then this is ensured that it gives you privacy. You don't need to know the details of that, but just know that this is what you're doing. Okay. So let's get a little bit more into details. So I can quantify that like quantity I told you by this key rate, basically, the rate on which I can tell you that how many bits of like actually good things I have, good bits of the key I have. So if you calculate that for QKD, it will give you this expression, which is easy to understand. So it's basically quantified by the entropy of the average error in the Z basis and in the X basis, right? I'll show you how I get that, but for now, let's stick with this formula. So if I assume that the error that happens in the X basis and Z basis are symmetrical, meaning that I have no particular reason to believe that Eve wants to bias, like attack one of the bases more than the other one, or for some reason like my protocol is biased, then I can put these values to be the same, and I can put them equal to the threshold I can tolerate, basically the Q bar, which I call D. So if I do that, I get this like more simple formula now. And now I can ask, what is the largest D that I can possibly have for a QKD protocol in general, right? No matter what Eve does. And I can answer that by saying that, okay, so the rate at which I get no key is what? Is when R is equal to 0. It means that then I have no bits of key left that I can trust. So if I put R equal to 0, I get the other variable in this equation, which is D, and that will quantify my Q bar. So if you do that, you get the 11% that you saw earlier. So that's where the 11% comes from. Okay, all good? So how do I get this formula in the first place? So this is a bit harder, but because of the things I told you, like intuitively at least it's not that bad. So basically this is actually that, right? So this rate is the mutual information, classical mutual information between Alice and Bob, minus the quantum mutual information between Alice and Eve. Why I have quantum here? The reason is that the things that Eve has quantum state in it. So you cannot talk about the information of Eve without quantifying those quantum states. So basically, this is quantified. So in order to be able to talk about like all the things that Eve can do, you put all the classical information together with some quantum information, like the quantum states that are being sent over the channel, and you construct this like big states that people call quantum classical state. It's basically all the classical information between. And then what you need to show is that how much information possibly Eve can extract out of this state. So from everything classical that she knows, and from all the states that are being transmitted over the channel, what is the maximum amount of information I can extract? Okay, so this is a quantity which we call accessible information. This is bounded by another quantity that we call whole-level quantity. Whole-level has done a lot of work in this field. And this is basically the maximum amount of information you can, so it's constructed from the maximum amount of information you can extract from one single qubit. And this value is less than 2, it's basically 1. Which is very important because a lot of people think that because qubits, they can be in any direction, they can contain a lot of information. But actually, Holever formally showed that you cannot extract more than 1 bit of information from a general quantum bit. So like the amount of information that's accessible to us as classical beings is still 1. And then you can use that to quantify that accessible information for the whole big bit string. Oops, I'm almost done. I have a bit of time. Okay. I have many slides. Then the full chain of inequality you need to go through to basically get here is that you bound this by accessible information, you bound accessible information by Holever quantity. You can write that the full Holever quantity as the entropy of this quantum state Eve has, plus the bias you have, the bias of information you have in these spaces, which is basically these 2 entropies. And if you do that, you do the calculation, you get here. Really nice and easy. So you just need to know how to quantify it. If you do, then it becomes easy. Yeah, and this is my last slide basically for today. So the proof I showed you, it's nice and rigorous. It's a full proof. It's not like the 1-by-1 attack system that I was showing you before. It actually quantifies everything that Eve can do. But it's an old proof, and they're better proof. And this has some issues. First of all, I made a lot of simplification assumptions. I assumed perfect measurements, perfect preparation for this. Because the quantities that I used is like accessible information and entropy and stuff, in the way that I use them, they only hold for when n is very large. So in the asymptotic limit, I cannot claim that this proof works for finite size keys. It's kind of like gives you an intuition that it should work, but it's not like exactly there. Then this proof is not composable. Composability is a very nice property we have in cryptography. What it tells you is that if you do a composable proof, when you combine this scheme with another scheme, you have the guarantee that it will remain secure. This is not generally true in cryptography. Like you can have something that you prove is secure, is completely secure. The moment you combine it with something else, it breaks, right? So composability, if you want to use a protocol as a subroutine of another protocol, it becomes very important. And this proof that I showed you, it doesn't have this property. It doesn't mean that QKD is not composable. It means that my proof doesn't show that it is composable. And then I consider that attacks are only relevant like bit by bit. So there's nothing much better I can do if I have the full string because my random variables were IID, which again is an assumption that you can do better. So you can like have collective attacks. And then there are some physical things that I didn't take into account. Like for instance, if bits get lost on the way, or if my detector goes dark for some of the qubits and things like that. Or if my source, if I want to get 1 qubit, it just like initially produces 2. Actually, the last one, there's no way to prevent it. So this is one of the bad things about QKD, let's say. There's like almost no way of doing that. You just like need to make sure your devices doesn't do this. Yes, and yeah. So the thing is that there are better proofs, though those are more complicated. So in the next lecture, I will give you the idea of what those proofs are, because I think the ideas are very insightful, so you get like something out of it. I will not go through like line by line proof of the new version of the QKD, but just to tell you that like how you can get around these problems. And I think that's it.
Question? Yeah.
Please, I'm not so far from Mina.
Please, thank you very much for your talk. I have just a naive question. What about the security of the full implementation? I mean, from calibration process, you should use some test integrity to be sure that everything is okay, to avoid all the auxiliary channels, etc. use full quantum components in your real life. How do you deploy such countermeasures in some sense? Thank you.
Yeah, thanks. That's a very, very good question. So these things I told you, like even the ones that I'm going to go around in the next proof, it's not a full proof of physical implementation, because usually it's hard to do proofs in that level. So you do the proofs with as less assumption as possible as you can, so that your proof generalizes to those scenarios as well. So this is the idea. So some of these things are actually like lossy channel, dark count. These are physical attacks, but you can integrate them into the proof. Some of the things like what you said is not so much. So there's a big body of research in the QKD community called side channel attacks, and this is basically what you say. So people try to understand what are these like side channel information you can extract, and what are the ways to prevent them. There is a recent work on basically some like nice properties of decoy state, which people like, it's a particular set of state people use for QKD. And I think, and this is very recent, and this is the first time people have like managed to get like some formal nice security proof for that. Before that, it was more like heuristic. You have to do some tests and then show that you pass the thing. The good thing is that you can always in the lab, whatever happens, you can compare it with the QBER, so you can get a sense of like if you're actually doing a good job or a bad job. So that's also one thing. But yeah, this is a lot of part of the field goes into doing what you said.
Another question for Mina?
Hello, thank you for the lecture. I was wondering about the principle of the QKD. You said that Alice wanted to send AI bits, a string of AI bits. So the goal is for Bob to have the full string of bits. Is that it?
So the goal is that Alice and Bob, at the end of the protocol, they have a bit string that matches. So the one that Alice has is the same as the one that Bob has. And that bit string is unknown to Eve. So Eve has no information about that bit string, or as least possible information. So QKD is not an encryption, it's just the way to get that bit string. And if you want to do encryption, then you can use the classical one-time pad. Like once you've done QKD, you have that like, long key that I showed you that you need for one-time pad, and then you can just do one-time pad. So if you do these two things, then you get information theoretic security, because QKD is information theoretically secure. One-time pad is information theoretically secure, and especially if they're composable, then you get full information theoretic security.
Yeah, so among the bits, the AI bits sending, only a few of them are
exactly.
Matter. Okay.
So statistically, you throw away half of the bits that half of the qubits that you communicate.
Okay.
And you only keep that, and it's even less than that, right? So then out of that, you use some of that for test, for the parameter estimation, and you throw away some, and then you do a hash function. It kind of like compresses it a little bit more, so you get less and less and less. Yeah. But this is still good enough, and you can argue that, okay, if I can do this length, why not more? And then you can expand and get a key size that's good for you eventually.
Yeah. Okay. Yeah. Thank you.
Another question for Mina?
Hi, thank you for the talk. It was really interesting. So, if I understood correctly, so ED has a 25% of probability of being detected between the communication, right?
In one of the attacks.
Yeah.
But in the general proof that I showed you, that threshold is 11%. So like,
okay.
It's better. So the lower the QBER is better. The protocol is better. Yeah.
So probably you have already mentioned, but probably I didn't catch it. But do you have a lower bound in the case of a noisy channel? So I mean, because for example, in the case of a noisy channel, EV, I guess could escape, could be undetected, or could be more detected depending on the noisy channel, because if you introduce some errors, some noisy gates or noisy channels in the communication, probably, EV can be the...
That's a very good question. So one thing that's like really nice in dealing things in this like information theory, in this like entropic regime, so using this entropic quantity, is that you don't need to distinguish between noise and adversary because you cannot in the real life, right? So when you get, let's say, a wrong bit, it could be that it's just because of noise, the bit flipped, or it can be that actually like Eve has messed up with it, and you need to kind of like distinguish that. And in real life you can, but the thing is that the good thing about this like entropic thing is that it captures both of the scenario. But you're right that in actual, like in real life, and that's why the rate for the real protocol are lower than the theoretical one, because you even, you have a lot of noise on the channel, and if you want to be tolerant to those, then you also increase the possibility of ignoring that you have an Eve on the channel. So you have to be a bit, so you have to throw away more things, let's say, when you have noise.
And so before lunch, well, maybe just mentioning that maybe some items that you can add here, if you think about real deployment, is how you do the classical authentication.
Yeah, I will talk about that a little bit in the next lecture. So because that was important, I'll talk about that.
And okay, so let's thank Mina again and go to